Welcome to the deep dive. So today we've got some interesting material practice questions, actually, for the D-ISM-FN-01 exam.
Yeah, and the explanations that go with them. A good set to dig into.
Exactly, because anyone can just look up answers,
Yeah.
but we want to, unpack the ideas behind them.
Get to the why. Understand the actual storage tech concepts these questions are testing.
That's the mission. A clearer picture of what's going on in storage today. So let's jump right in.
Sounds good.
Okay, first up, a question about RAID levels. It asks, which RAID level provides the best performance for write-intensive applications while still offering data protection? Options were 0, 1, 5, and 10.
And the answer given is RAID 10.
Right, RAID 10. So for folks maybe less familiar, why is RAID 10 the pick here, especially for write-heavy stuff?
Well, RAID 10 basically combines two other levels. It takes RAID 0, which is striping for speed.
Spreading the data out.
Exactly. And it combines that with RAID 1, which is mirroring for redundancy.
So a copy of everything.
Right. You get the right performance boost from striping, but if a drive fails, you've got that mirrored copy ready to go. It kind of hits that sweet spot between speed and safety.
Okay, speed and safety.
Yeah.
But there's a catch, isn't there? Cost.
Definitely. You need at least 4 drives to even start with RAID 10. And because of the mirroring, you only get half the total raw capacity for actual use.
So it performs great, protects well, but it's not the most space efficient.
Precisely. It's a trade-off. You pay for that performance and protection in usable capacity.
Makes sense. Okay, let's move to question 2. This one's about block storage. What component manages physical storage and presents logical storage to hosts? Options: volume manager, storage processor, HBA, file system.
And the answer is A, the volume manager.
Volume manager. So what's its main job? What power does it give you?
Think of it as an abstraction layer. It sits between the physical disks and the servers, the hosts.
Okay.
It pools the physical storage, all those individual drives, and lets you carve out logical volumes from that pool.
So the server just sees a drive, not all the complicated bits underneath.
Exactly. And the real power is flexibility. You can resize those logical volumes, you can mirror them, combine disks, all managed by the volume manager software.
Without messing with the applications using the storage.
Generally, yes. It makes managing the underlying physical complexity much, much easier, more agile.
Got it. Abstraction and flexibility. Yeah. Next up, question 3 dives into object storage. What's the primary purpose of metadata in object storage?
Right. The options included network stuff, block location, describing data properties, and user tracking.
And the correct one is C. To describe and manage the properties of stored data. We hear metadata mentioned a lot with object storage, like for cloud backups and things. Why is it so central?
Okay, so unlike traditional file systems, with folders inside folders.
Hierarchy.
Yeah. Object storage is flat. Everything exists as an object in a huge pool. There's no folder structure.
So how do you find anything or manage it?
That's where metadata comes in. Each object has metadata attached to it. And this isn't just basic stuff like file name and size.
It's more detailed.
Much more. It can include who owns it, when it was created, access policies, maybe content type, and even custom tags you define yourself.
Custom tags, okay.
And that rich metadata is what lets you search, manage, and retrieve potentially billions or trillions of objects efficiently, even without folders. It provides the context.
Right, the context and the handles for managing all that unstructured data. Okay, let's talk efficiency. Question 4 asks about provisioning. Which storage provisioning technique allocates storage only when data is written? Options: static, thin, thick, direct.
And the answer here is B, thin provisioning.
Thin provisioning. Sounds efficient. How does that allocate when written part actually work? How does it save space?
Okay, think about traditional or thick provisioning first. If you tell a server it has 100 gigs of storage,
Yeah.
with thick provisioning, that 100 gigs of physical disk space is immediately reserved, locked away, even if the server only uses, say, 10 gigs right now.
So 90 gigs are just sitting there unused but allocated?
Exactly. Wasted, potentially. Thin provisioning flips that. It tells the server it has 100 gigs, but it only actually grabs physical space from the storage pool as the server writes data.
On demand.
Precisely. So that initial 10 gigs uses 10 gigs of physical space. If it writes another 5, it uses another 5. You're allocating just in time.
That sounds way better for utilization. Any downsides?
The main thing is you need to monitor carefully, since you're potentially promising more storage than you physically have right now.
Oversubscribing.
Right. You need good monitoring to make sure you don't actually run out of physical space when applications suddenly need the capacity they were promised. But managed well, it saves a lot of capacity up front.
Okay. Pay-as-you-go storage, basically. Makes sense. Question 5. Software-defined storage, or SDS. What is a benefit of SDS? Options touched on hardware, coupling, abstraction scalability, and automation limits.
And the answer highlighted is C. It abstracts storage resources for better scalability.
Abstracts again. So SDS separates the storage software, the brains, from the actual hardware boxes.
That's the core idea, yeah. Decoupling the control plane, the management software, from the data plane, the physical storage hardware.
And why is that a big deal? What's the benefit?
Flexibility, mainly, and scalability. Because the intelligence is in the software, it can potentially manage lots of different types of hardware, even standard off-the-shelf servers, commodity hardware.
So you're not locked into one vendor's specific storage arrays.
Less so, yes. You can often scale out more easily, maybe more cost-effectively, by adding standard hardware managed by the SDS software. It also usually brings better automation and programmability to storage management.
More freedom, more automation. Got it. Let's shift gears to the cloud. Question 6. Which cloud feature allows automatic scaling of resources based on demand? Options: multi-tenancy, self-service, pooling, elasticity.
The answer is D, elasticity.
Elasticity. We hear this word constantly with cloud. What does it actually mean in practice?
It's one of the cloud's real superpowers. It means the platform can automatically add or remove resources, compute power, storage, network bandwidth, based on the actual workload demand.
So if my website suddenly gets hammered with traffic,
Elasticity kicks in. The cloud platform automatically spins up more web server instances, maybe allocates more database resources, whatever is needed to handle the load.
and then scales back down when traffic drops.
Exactly. It scales down automatically, too, so you're not paying for resources you aren't using during quiet periods.
Dynamic adjustment. Very efficient.
Okay.
Okay, now for speed. Question 7 is about NVMe over fabrics, or NVMe of F. What describes a characteristic? Options involved HDDs, file-only, latency reduction, tape.
And the answer is C, reduces latency by accessing flash storage over networks.
NVMe itself is fast, right? For local flash drives.
Incredibly fast. It was designed specifically for flash, unlike older protocols like SATA or SAS, which were designed for spinning disks, lower latency, higher throughput.
So NVMe takes that speed
Yep.
and puts it on the network.
Essentially, yes. It extends the NVMe protocol across network fabrics, could be Ethernet, could be fiber channel. It lets servers access shared NVMe flash storage over the network with latency that's much, much lower than traditional storage networking.
Almost like it's local?
Getting very close to local performance, but with the benefits of shared storage. It's a huge deal for performance-sensitive applications, databases, AML, analytics.
Anything that needs really fast access to lots of data. Okay. Question 8 brings us to virtualization. Which component manages multiple VMs on a physical server? Options: container engine, hypervisor, management console, file system agent.
Answer B, hypervisor.
The hypervisor. What's its fundamental role?
The hypervisor is that crucial software layer. Sometimes it's firmware that actually creates and runs virtual machines.
It sits between the hardware and the VMs.
Right. It takes the physical server's resources, CPU, RAM, network, storage, and divides them up, allocating slices to each VM.
And keeps them separate.
Critically, yes, it provides isolation. So one VM crashing doesn't take down the others on the same box. It's the foundation of server virtualization.
The ringmaster for the VMs. Got it. Question 9, back to object storage. What key feature makes object storage good for unstructured data? Options mentioned: LENs, RAID, blocks, and then metadata flat namespace.
And D is the answer. Enables custom metadata and flat namespace.
We talked about metadata, but that flat namespace part, why is that specifically good for, say, huge libraries of photos or videos?
Because you don't have that rigid folder hierarchy anymore. In a flat namespace, every object just lives in one giant pool, identified by a unique ID or key.
No navigating through folders.
Nope, you access it directly via its key. And when you combine that direct access with the ability to attach really rich custom metadata.
Like tags describing the photo content, maybe?
Exactly, or video length, or sensor data type, whatever. It makes it incredibly scalable and flexible for managing massive amounts of data where a folder structure just wouldn't work well or would become impossibly complex. Search and management are driven by the metadata, not the location.
A much more modern way to handle unstructured stuff. Okay, final question. Number 10, data protection focus. Which technology provides continuous replication by capturing every write operation in real time? Options: snapshot, async, CDP, disk mirroring.
Answer C, continuous data protection, or CDP.
CDP. How is that different from, say, snapshots or regular replication?
Snapshots are point-in-time copies. You take one now, another one in an hour. Asynchronous replication copies data, but usually with a slight delay.
Okay.
CDP is, well, continuous. It monitors every single write I/O as it happens on the primary storage.
Every single one.
Every single one. And replicates it immediately or near immediately to a secondary location, often keeping a journal of these changes.
Wow. So what does that give you in terms of recovery?
It means you can potentially recover to any point in time, not just the last snapshot or the last async replication cycle. If something goes wrong at 10.37.15 a.m., you can often roll back to 10.37.14 a.m.
So minimal, potentially near zero, data loss.
That's the goal. It offers a very granular recovery point objective, which is crucial for really critical applications where any data loss is unacceptable.
That sounds incredibly powerful for critical systems. Considering this whole spectrum we've just discussed, performance, protection, cost, scalability, management. When you're designing storage for different needs today, what factors do you think end up being the most critical? Is there one that consistently bubbles to the top, or is it always just?
Yeah, it depends.
That's the million-dollar question, isn't it?
Definitely something to think about.
Yeah.
Until next time, keep exploring.